Okay, so again, thank you for the invitation. It's really nice to be part of this. So today, just like Diego, I'm going to talk about fractional time derivatives, but I'm going to connect that with some function which is called Herglotz-Nevanlinna function. So this is a class of functions which has been studied for decades in the context of operator theory and complex analysis. Okay, so we'll see how these two can be combined together and actually get something very useful out of it. This research is partially sponsored by USNSF and partially by the EU XPower project, which Johan mentioned. Okay, so the outline of the talk is I'm going to give you a one-slide introduction of the scalar valued Herglotz-Nevanlinna function. I put scalar valued here because it can also have operator valued or matrix valued Herglotz-Nevanlinna function. And I'll also focus on a special class of this Herglotz-Nevanlinna function, which is a Stieltjes function, because it has a very useful interpolation property. And then after that, I'm going to switch gear to something very applied. So where you will see fractional time derivative. And I'm going to give you some background about why it is there, and it's related to anomalous diffusion. So I'm going to explain to see where does it come from, right? So mathematically, what does it mean? And then, so after seeing that, like Diego mentioned, when you want to develop a time domain solver, you need to do marching in time. So to deal with the integral, you need some quadrature rule. So in my talk, the quadrature will be based on the theory from Herglotz-Nevanlinna function, and then conclusion. So let's start. So this is my one-page slide. Let me move this a bit. Okay, this is my one-page slide. Okay, so as you can see, so this is an introduction of Herglotz-Nevanlinna function, and it has a lot of names. It can be called R function, peak function, depends on whether you look at the upper half plane or you look at the interior of a unit disk. Okay, so in my notation, I stick to the half plane. So C plus and C minus. C plus corresponds to the upper half plane, and C minus corresponds to the lower half plane on the complex plane. And I have a function M. M is a function which is just has to be defined on the upper half plane, and it's a complex value function. And this function will be called a Herglotz-Nevanlinna function if this function M is analytic on the upper half plane. So number one, so Herglotz-Nevanlinna function, first of all, has to be analytic on the upper half. Okay, and it maps upper half to upper half. So the second line here simply tells you to be qualified as a Herglotz-Nevanlinna function, this function will map the upper half plane to upper half plane. Okay, it can also have 0, but that's it. So a Herglotz-Nevanlinna function, by definition, cannot map points on the upper half to lower half. So the reason, and it can have singularity, but all singularities of a Herglotz-Nevanlinna function will have to be on the real line because it has to be analytic on the upper half plane. Yes, and from the definition, okay, so it's very simple, right? Upper half to upper half, analytic in the upper half plane. This is what a Herglotz-Nevanlinna function is. But for me, the beautiful part, amazing part of it is if it's a Herglotz-Nevanlinna function, then the following representation holds. So that means if it's a function simply defined here, then if M is a Herglotz-Nevanlinna function, which is defined on the upper half plane, then there will exist real number C, a real number D, and a Borel measure, D mu, is a positive Borel measure here, such that the Herglotz-Nevanlinna function can be represented as this linear part plus this integral part, right? As you can see, the dependence of Z is in this integrand. So there's a measure which is independent of your choice of Z. So with every Herglotz-Nevanlinna function can be identified with C, D, and this Borel measure. Okay, and as you can see, because of this representation, even though the Herglotz-Nevanlinna function is only defined on the upper half plane by definition, I can easily extend it to the lower half because C, D, and this lambda and this mu are real value, right? So I can just take complex conjugate and then get this symmetry. So this tells me if I have a function value on the upper half plane, then I take the complex conjugate, then I will get its value on the lower half plane, right? The complex conjugate point. So this is a symmetry of Herglotz-Nevanlinna function. And in general, this Borel measure here will not have finite mass. Yes. So so you have to be weighted by 1 plus lambda square. And okay, hold on, let me see. Can you still hear me?
Yes, yes.
Okay, good. It's very quiet. I want to make sure there's no disconnection. Okay. And okay, so you say, okay, then okay, what is a Stieltjes function? So if this, you see, so this one, because this has to be weighted to have finite mass for this measure. Yeah. So in application, it's not so easy to use. However, a special class of Herglotz-Nevanlinna is the following. It's called Stieltjes function. So that means if this Herglotz-Nevanlinna function, on top of being a Herglotz-Nevanlinna, if it decays fast enough along the imaginary axis, you see, so this is M evaluated on the imaginary axis, yes, and multiplied by the Y. So if in the end, you look at a supremum, if it lasts than infinity, then this representation will boil down to something very simple. So it will just be this integral term. Not only that, this Borel measure here will have finite mass. Yeah? So if it decays fast enough on the imaginary axis in this way, in this sense, then the function is called Stieltjes function. And the Stieltjes function can be identified with its corresponding Borel measure. That's it. And this integrand is very simple, 1 over lambda minus z. Okay, so the question you can easily ask is, why do people study this? People study this for decades was because this is related to causality in physics. So the future can only depend on the past, right? It cannot be the opposite. So the way they think about it, I believe, is upper half means the future. So you have future mapped to future. So this is a mathematician's way to say causality in physics. And why? So this makes it very useful. Okay, so we'll see why. Okay, so let's see if I can move to the next slide. Okay, so like what I said, so why do I care if there's a Stieltjes function? Because in 1978, in Gelfand's thesis, he proved something really nice. In what sense? So see, think about the definition. If I have a Stieltjes function, it's very nice. It's analytic on the upper half plane, but its singularity can be anything you want it to be on the real axis. It doesn't even have to be isolated singularity. It can be a branch cut or whatever it is. However, in 1978, he proved that if it's a Stieltjes function, then if you consider the rational function approximation of this Stieltjes function, so the rational approximation, the numerator is n-1 polynomial on top, and denominator is n polynomial at the bottom. So think about this n-1/n approximation of a Stieltjes function. So in his thesis, he proved the following. Okay, number one, so I can interpolate, say, okay, so what are the cases? So you can interpolate on real values as long as you don't touch the singularity, which has to be on a real line. If you use interpolation points, 2n of them, okay, so what I want to focus here, this is an interpolation, just write down interpolation. What I want to focus on is this, what I mark as red. So this theory tells you if you want to interpolate a Stieltjes function, if you interpolate at a complex value, means the imaginary part is not zero, you call zj. I interpolate at zj. Then you should also interpolate at zj bar, the complex value. Okay, so that's one. If you do this, yeah, and then of course you can interpolate on the real value, also infinity. So I'm not going, this is not important for my talk. So then once you interpolate this way, then he proved that this, I mark as blue here, this n-1/n rational function approximation for the still just function, which I define this way, itself is also a still just function. Okay, so because there will exist a particle measure beta to make this happen. Okay, and the most important thing is what I put at the bottom here. So even though your still just function can have any type of singularity on you want on the real line, however, its rational approximation of the still just function must have simple pole. So this is something very important in application. So he proved it. So the summary of this slide is rational function approximation of a still just function if you respect this way of taking interpolation points. Then you see, you get this n-1 polynomial over n polynomial. You do partial fraction decomposition. Theory guarantees that all the poles will be simple. And all the poles here will fall in the range of the original singularity of this still just function. And RK I co-residue here are guaranteed to be positive. Okay, so these are real. So poles and residue are real, and all the poles will be located within the original range of this singularity of this original function. Of course, this n depends on how accurate you want that to be. So n is the number of interpolation points. What? Okay, why? Well, because if you give me n, I can generate the other n by just taking the complex conjugate by using symmetry. So this is just a detail. Okay, so the point is, if I have a still just function, I can do interpolation very well. And there are several schemes I can use. Okay, so I'm going to switch gear to the apply side. So this slide, as you can see, what you identify in all of these pictures is it has quite complicated microstructure. So now imagine, so now sandstone, industrial material, the some foam, and sea ice. So this is I believe the yellow parts are the pore space of things, and so that's where the seawater can sit through. And here is the bone. So just imagine, so now this is a bone structure. So in living body, all these pore spaces are filled with viscous fluid. So now we will to see time fractional derivative, just try to imagine something is diffusing in this pore space. So this pore space has some viscous material, and suppose some chemicals are diffusing in this very complicated pore space. So this is so then you will see some phenomena which is slightly different from the usual diffusion equation we are very familiar with. Right. So what is it? So now you see this microstructure caused by this very complicated structure of the material. A lot of physics, for example, diffusion, will have to be modified. In what sense? I'm going to use this slide to say something about it. So I'm going to call the chemical which is diffusing as U, the concentrations. U, of course, depends on space and depends on time. And the usual diffusion equation, as we know it, is this, right? Partial TU, the time derivative of U, is related to a coefficient, diffusion coefficient times Laplacian of U. So this is the usual diffusion equation we know. And then it's proved by, okay, so this diffusion equation, what we observe in the macroscopic level actually is a result of what happened in the microscopic level, because when the chemicals are diffusing, it get bumped by all the surrounding molecules, right? That's why things are diffusing. So it's discovered, I don't know who was the first one. I believe Einstein was one of the first to establish a theoretical relation between the diffusion equation you see here and random walk. So if you look at this diffusion equation as a collective result of a lot of particles doing random walk in the microscopic level, then now let me fix the notation here. Okay, so now here, so just imagine you have a lot of IID, a lot of particles moving independently. Yes. So now you say, okay, so now I look at them, they are doing this random Brownian motion. Okay, so Markovian random walk. And then you compute for each one of them. So xt is the current position of one Brownian particle. So you take the expectation value of the square because you don't want them to cancel, right? The square, and you look at that. So if this is a standard Brownian motion, then this expectation value of this mean square displacement will be 2 times the dimension times the viscosity times the d coefficient times the time. Yes. So the point is, in a standard Brownian motion, the mean square displacement will be proportional to t to the 1, to the first power. So in this setting, if you upscale that to the microscopic level, you will get the diffusion equation. Okay, yes. So now this is when the random walk has no constraint, just move anywhere they want it to go, right? So it's t to the 1. However, imagine now, if diffusion, if this particle has to do random walk in a very complicated pore space, which I show you, then it's well studied that, hold on, where is it? Yeah, here. So, okay, so now because the particle will hit the wall, sometimes will stay on the wall before it go back to the fluid again. So then this is no longer just proportional to t to the 1, it's t to the alpha. Okay, so alpha, if alpha is between 0 and 1, means it's smaller than 1, then that means it doesn't move as much as the usual one. So that's why it's called subdiffusion. Yes. And sometimes for some reason, in a different setting, not this microstructure, alpha can be greater than 1. It's called superdiffusion because it travels more than the usual random motion. So I'm going to focus on this subdiffusion here, because just like also in Diego's talk, you also see his alpha is between 0 and 1. I think you can explain that in the context of diffusion to be, this is the result of this very complicated structure all these particles have to walk through. Okay, so this is a microscopic level. For this kind of random walk, theoretically, in the context of stochastic differential equation, you can prove theoretically, like rigorously, if you upscale to the macroscopic level, your diffusion equation, like this one, will no longer hold, right? This one is partial TU. If you have a subdiffusion in the microscopic level is this, then it will show up in your diffusion equation. Okay, so there are 2 choices, 4 and 5. Okay, 4, this one is the Riemann-Liouville derivative Diego also mentioned. So this one, and then, okay, and I put the definition here. So this is less regular than the Caputo. So I'm going to focus on Caputo because these 2, so you can write this way as well. You can write either this way or you can write this way. So this way, let me focus on this way because this is more transparent. Number 5, instead of partial TU, this diffusion equation, the partial TU part will be replaced by this Caputo derivative. Caputo, and then the Laplacian part is the same. And I put a source term there. So there's a source which create a chemical and then it will diffuse in the media. Okay. So this Caputo derivative, let's have a close look at this. So this Caputo derivative, indeed, it is an integral. So what is that? Caputo derivative is a convolution of this kernel, t minus s to the minus alpha. If it's Caputo derivative order alpha, the kernel here is minus alpha. So it's a weakly singular kernel. But it's convoluting not with v, but partial SV. So time derivative of v. So Caputo, if you want to have a Caputo derivative, the traditional derivative of the function has to exist for this to be well defined. Okay. But remember, Caputo derivative is acting on time derivative of v. Okay, so as a mathematician, so what is this, right? So when people model it, what does that really mean? So this is where the Herglotz-Nevanlinna function will come in to help us. The focus is on this kernel, and this gamma is a usual gamma function evaluated 1 minus alpha. Okay, so Caputo derivative. So now imagine you have to solve this problem in time domain, and this is tricky because you have a memory term here. How do you discretize in time? And another bad thing is if you have a memory term, if I want to solve at time t, I will have to store all my solution u, right? up to this point to see. So you will have to use a lot of memory to do it. And memory is very expensive when you do computation. Yeah, you don't want to store your solution all the way to the time you want to march from. So it's a reason. Okay, so I'm going to focus on this subdiffusion. I just copied from the previous slide. So suppose now I want to solve this problem in time domain and with a given initial condition. And I suppose I'm solving in, I don't worry about the boundary, yes? So initially, this is the initial concentration. I want to march from here to go forward. Okay, so I will claim that I can, without loss of generality, yeah, we really always like saying this, by assuming this initial value is 0. Why? Well, because the good thing is Caputo derivative of a constant function, constant with respect to time. Caputo derivative of a constant function is 0. But this is not the case for other like Riemann-Liouville. The Caputo derivative, no, the Riemann-Liouville of constant function is not 0. So let's create some problem in some kind of regularity. But for Caputo derivative of a constant is 0. Therefore, if I have this, and this is Caputo, right? I just subtract this one from this and call a new variable, and then absorb the term into the source term. So I can do it. So I'm going to say without loss of generality, in the slides from starting from here, I will assume U0 is 0. Okay. So now what do? Okay, so let's take one more look of this. Okay, this Caputo derivative, and this is a kernel. So when we deal with things like this, we think about, sorry for this, what is this? Okay, yes. So, okay, so let me skip this. I prepared this for Diego, but I'll show him later. Okay. So now let's look how we handle that. Okay, so when we have a convolution term, we think of transform. When I go to the transform domain, the frequency domain, then I will be dealing with a product. So here I define this Fourier Laplace transform of the kernel function. So if you just forget, if you don't worry about this one, you take Laplace transform. And I'm transforming at z equals minus I omega. So if I look at this side, this is just like halfway Fourier transform, right? So it will be e to the I omega f of t dt. So this is the usual Fourier transform, maybe with a sign difference between other people's definition. So this will be defined as my hat here. So this is a so-called Fourier Laplace transform of a function. So essentially, this is a half Fourier transform. We call Fourier Laplace transform. So let's see how will this help us. So now if you go back to look at this Caputo kernel, another piece of information is Caputo kernel will involve this function, which is something to the negative power. This power is between 0 and 1. So it is well known that Laplace transform of t to the beta, so I call beta now. Beta is alpha minus 1. So Laplace transform of this function is z to the beta plus 1 with a gamma function on top. So this is well known. So now if I Laplace transform Caputo derivative, what I will get is the kernel will give me 1 over z, will give me this one, z1 minus alpha. Yeah, this one, okay, and then this Laplace transform of this derivative get this one. This is just the property of Laplace transform. And then because I assume this is 0, so it's not even going to be here. Yes. So now the idea is the following. The idea is, okay, so now this is a kernel. So the Laplace transform of Caputo derivative looks like this in the transform domain. So what can I do about it? Okay, so this z, okay, another thing to notice is this z to alpha minus 1, because alpha is between 0 and 1 for subdiffusion. This alpha minus 1 will be in this range. Will be a negative number, but not too bad. Will be greater than minus 1. Yes. So my goal here is the following. I say, okay, so this is a kernel. Can I do this? That's my goal. And I'll just justify that later. I say, okay, in the transform domain, can I approximate this Caputo kernel in this way? So I'm asking a lot here. So I want to approximate this Caputo kernel with a number A0, which is the real number, plus a sum of n pairs of something, which will look like A. So it's AK divided by K. So divided by this one. Hey, sorry, my mouse is very, very sensitive today. Hold on. Okay, here. Yeah, so I want to approximate this way. Remember this A0, I want it to be real. I want this AK to be positive, real number. I want this BK to be also positive. And not only that, I want all this BK to be different. I don't want to have any non-simple poles. Okay, so if I can do this, can I do this? I will show you, yes, you can prove it. But why let me explain to you why I want this. So if I can replace a Caputo kernel with this number plus all of this, yeah, then what happened? Why do I want to do this? I want this one, yeah, that's what I want. I want all the BK to be distinct, different. Then I want this one because simple calculation here, Laplace transform of Caputo, I just replace this one with the approximation I want here. And this is this is the Z, this has to be there, yes, and this is 0. So I do very simple algebra, So in the end, I get line 10. So in the transform domain, if I have this approximation, then the Laplace transform of Caputo will just be a real number times ZU transform plus this and plus this. So, but then I can go back to time domain and ask myself, what do I get in the time domain? So I transform back to time domain. This term will give me A0, which is a real number, times first derivative. Okay, so I have A0 times the usual time derivative, plus this one. This one transformed to time domain will be the sum of this positive number. So this will be a positive real number times the U itself. Okay, so in physics, this will give me some sink on the other side. And this one, if I transform back to the time domain, we know very well the inverse transform of this one is BK times e to the minus BKT. So this is related to the exponential function, relaxation time. And my BK, remember, this is why I want the BK to be negative. So it's a relaxation time. So it's stable, it's not exponential growing, yeah? So the BK is positive, then all of this will be decaying. So it fits into the physics of relaxation time. However, inevitably, you say, well, I still have a memory term here. Yes, I still have a memory term. So the punchline here is, as a mathematician, we think, okay, what is a Caputo derivative? What Caputo derivative does for this alpha is actually for subdiffusion. It gives you a number times the usual derivative plus a number times U itself and subtract these kernels. This is what Caputo derivative does. It does still contain the usual derivative, but it's multiplied by a number. This number has to be determined by the approximation. If I have this approximation, yes? So once I have this, they go to the auxiliary variable. So now with the Caputo derivative, I write back to the time domain. And then at this point, it's very clear which I should do. So I will just call this, still have the memory term, but this time the kernel is much simpler. So you just call this as suppose you have n terms to approximate your rational function. Each one of them, you just call them psi k. And you just throw the entire memory term into this unknown. So your unknown psi k is just e to the minus bk convolute with your unknown u, which is the concentration, yes? But then the price is very low when you do this. You define this way, it's very clear. This new variable satisfies this ODE. Because I say ODE is because there is no spatial derivative here. So numerically, when you solve it, you are using the space as just a parameter. So this is the ODE. So the price you pay by doing this transform is if you try to approximate the function with n terms, you have to throw in n auxiliary variables. But each one of them solve a very simple ODE whose coefficients depends on the BK you just found in your approximation. Yes. So then now to rewrite this, so now if I want to solve this problem, the subdiffusion problem, what I will do is I will do this. Now you don't no longer see any memory terms explicitly, because those memory effect now is carried by this auxiliary variable. So you just carry this psi k along by adding these n ODE into your system and you solve it, just like the usual way you solve a differential equation. Okay, so this is this is the scheme. But the question is, as mathematician, we would like to know, well, is this really possible? If so, why is it possible, right? Is it possible? So I'm going to fix the notation here to make it easier. So now I'm looking at this subdiffusion. So my alpha is between 0, 1. I'm calling this number to be my beta, okay? And remember, I copied from previous slides. I want this. Okay, this should be a real number. Okay, from my previous slide. So now, okay, so can I do this? So where is Herglotz-Nevanlinna function? Okay, so you don't have to, okay, so Herglotz-Nevanlinna function, we can show that this function indeed is a Herglotz-Nevanlinna function. I can even write the Borel measure here. So for Herglotz-Nevanlinna, it's a Herglotz-Nevanlinna function, and it has this representation, all right? But for this, in terms of computation, it's not useful. In what sense? You see the support of this measure here is infinite. So this, in terms of, I try to approximate this, the result is not good. Okay. So my goal is from here, can I see a Stieltjes function? Yeah, so if you use Herglotz-Nevanlinna straightforward, you'll get this one, but this is not useful. I need something better. Okay, so let me see, we do change your variables. Okay, so I'm going to transform this function, the kernel of Caputo derivative, into something which I know behave very well. Importantly, I want the support of the measure to be confined in a finite interval on the real axis. Okay, so here is what will work. I do a very simple transform. 1 over 1 minus z, the usual fractional linear transform. We teach students in the complex variable class. And then z beta can be written this way. Okay, so now see, let me go back. Okay, for the sake of clarity. Where is the singularity of z to the beta? Z to the beta, you need to take a branch cut. Yes, because related to the log function by definition, you have to take a branch cut. So if I don't do change of variable, the singularity of this function is a half line, right? Let's take the principal branch, minus infinity to 0. This is the original branch cut. So now if I transform this way, of course, if you transform this way, you look at this notation here, you can clearly see zeta equals 0 and zeta equal 1 are 2 branch points there. So you just choose branch carefully. And I'm going to just tell you the result. So you choose a branch carefully. After this transform, right, you transform your kernel to be in terms of zeta, which is beta. Then after this mapping, the branch cut on the zeta plane will be confined to 0, 1. Okay, confined to 0, 1. And the branch cut is exactly in 0, 1. So this branch cut after this, and then you say, well, what about other properties? So if you do things carefully, okay, so where is that? Okay, so this is my new function, yeah? So I want this function as it is not a Stieltjes function. What I'm aiming for, getting a Stieltjes function out of this. So this step solve the problem of unbounded branch cut, right? With this transform, the branch cut is confined in 0, 1. That's one thing, good. But I still have to check other properties to make sure I have a Stieltjes function. So the answer is here. You take this function, you negate it, plus 1. Then you can prove this function, defined this way, is a Stieltjes function. Okay. Now, and because you see it decays fast enough. Okay, you can prove it. So it is a Stieltjes function. So now my goal will be I take this, right? This is defined from my Caputo, right? And just kind of manipulate that a bit to see a still-just function. So now if I can approximate this, interpolate this function, then I get interpolation of my Caputo derivative. Yes? So for this one, so to do interpolation of still-just function, the capital G, because I'm thinking in terms of Fourier Laplace, this interpolation has to do a good job on these points, because these are the points which matters when I do Fourier transform. Yes, so these are the frequency. So how do you choose the frequency? There's a source term, so I need to do a good job for all the frequency content in the source function. Yes, so suppose this is a banded, suppose it's a finite band, no matter how wide it is. I have to do a good job there. So I do this interpolation point. And then I run my interpolation scheme. So this is a scheme called two-sided residue approximation for still-just function. So all you need to do is the following. You want to interpolate function G at these points. Yes. So now in my scheme, all this UI is just one. Okay, so they don't play any role. So you assign this to be the V. So V is your interpolated grid value. So you have the V. So you have N interpolation points, right? So my UI is 1, and then I know where I interpolate, right? My zeta, K, I interpolate at this point, right? Because this is the interpolation point on the Z domain, but remember I transform to zeta in order to get a still-just function. So this is where I interpolate. So where you interpolate and you form this combination of two matrices. Okay, these are the interpolation points, and the star or the bar, they simply means complex conjugate. And you form two matrices. And theoretically, it is known that these two matrices are self-adjoint. And one of them is, okay, S1 is positive definite, S2 is positive semi-definite. Why is this important? This is important because then what I do is, you can forget about all of this. I solve this problem. I form this S1, S2. Okay, this is the S1. I solve a generalized eigenvalue problem. S1 is positive definite. S2 is semi-definite. So this is a stable solver. So you can simply use the MATLAB to solve for the eigenvalues Y and eigenvector L. So you solve it, right? You solve it, and then you just call the what is this? The LKK, I'm sorry, so this must be eigenvalue. So you can harvest from this eigen pairs, okay, to do this. So you harvest from RK, DK, and remember I promised, I said I want the A0, AK, BK, yeah? Let's see, where is that? Here. Remember, I showed this because I want on this to see. So A0, AK, BK, so you have the previous scheme. You take the eigenvalue, eigenvector, you can compute this A0, AK, BK. Yes. And then remember I said I want this BK to be positive, so you can check all the signs. So all the signs, all the constraints I want in the approximation can be proved rigorously to be true. Yes. So this scheme will show you how to find that. Okay, so now let me show you how good or how bad the numerical result is. So now, like what I said, I'm trying alpha equals 0.3. Just pick any number from 0, 1. So I solved that. So beta is alpha minus 1. So I have to approximate this kernel well. So minus I omega to this one. Remember, and this is the form I want it to be. And with this eigensolver, simple MATLAB, this is the value. I use n equals 10. And so how far do I interpolate? So this inflation point is going from 1 to 10 to the, okay, let me see, where is it? I cannot see my screen here. Let me see. 6. So it's 7 degrees of magnitude here. I use 10 points. And then this is what I get. Yes. And how is the approximation? Okay. It's here. So here, so for this interpolation problem, so the red part is a approximation. the blue part is exact. So this is a real part. Let me see. This is a real part of the kernel of this one. It's the imaginary part of this kernel. As you can see, they are almost indistinguishable over from frequency 1 to 10 to the 6. The only thing, if you look very carefully, is only at near the corner here. You can see blue only around here, right? So now to have a clearer estimate of my error, I plotted here, relative error. So the relative error, if I plot it, so I do the difference divided by the magnitude of the exact. So on the left panel is this one. Yes, as you can see, at 1 is actually very small, 10 to the minus 12, but it has a small peak, small layer here, and then it will drop to 10 to the minus 6 relative accuracy. And if I plot the real part, where's the real part? Let me see. Real part is the blue, and blue is the real part, and red is the imaginary part. As you can see, it looks like this. So so this is so this one, I take the grid point to be equally spaced. If I take like logarithmically distributed, I get worse result. And things like this is not just isolated for this case. For still just function interpolation in my other work, I also observe that for this lower frequency, you have less good accuracy. So this leads to my conclusion and to my future work. So the future work will be, now I can interpolate at 10 points, right? So I'm working with actually also people in XPower project. We're trying to find the best places to put the grid points to bring down this relative error. Okay, but nevertheless, for most of the spectrum you see with 10 points to interpolate this 7 order of magnitude, mostly it's actually 10 to the minus 6. So that's a performance. And conclusion is the Herglotz-Nevanlinna function can handle time fractional derivative. And the reason is the following, because we can have different derivatives. We can have Riemann-Liouville, we can Caputo, we can have all other things. But no matter what they are, these kernel had to be causal if your system is passive. So this kernel, no matter what it looks like, it has to be a causal function. If it's a causal function, then it transform has to be a Herglotz-Nevanlinna function. Yeah, so then from there, you do change your variable, then you do still just. So this, even though I show you the result for Caputo, I believe it can be applied to other time fractional derivative. And thank you for your attention.
Thank you very much, Yvonne. So I will share your presentation also with Diego.
Yeah, great.
It was a bit unexpected, but good. So are there any questions from the audience? Paolo or?
No, it's very nice talk, very interesting.
Thank you.
I would like only to ask a courtesy to give best regards to Professor Shaw, George Shaw, and Professor Gilbert from Delaware University. You probably know them.
Did I see you before? Let's show me your face. I can only see the top of your face.
Yes.
Sean, where
yeah, several times.
Oh.
Several times, because
Small world.
they were close friends of Professor Piquera.
Yes,
and a pupil of Piquera. So I met several times in Italy.
Yes, no wonder.
Yes.
It's so nice. Yes, I'll pass your regards to them. They are both doing very well. They both retire, but they both are still busy. Yeah. Yeah, these two. They cannot stop.
They are working again. Thank you.
Small world.
Yes, it is.
I have a question.
Yes.
Yeah, could you back to your equation?
Okay.
So the equation with the fractional derivative.
Okay.
The original equation. It's no.
Yeah.
It's this one. Okay?
Yes.
Yeah. Use K is not time dependent. It is true.
Correct. You mean K, right? No, the coefficients are not time
Are
dependent.
not time dependent.
I mean, this K here,
Yes, yes.
no, in general, it's not, but it can be because, but it can be handled in the same way if it is time dependent. Because the whole thing I did was I tried to approximate this operator in the time domain. I did not transform the entire equation. The whole thing is I asked myself, okay, so if I want to make sense out of this operator as a mathematician, yeah, in time domain, what would that look like? So all I did was I transformed this Caputo derivative and approximate that in the transform domain, and I go back to time domain. I didn't touch this one.
Okay.
Yes.
Let us assume for the moment that it is not dependent on a time domain.
Yes.
The fractional derivative you have there as an eigenfunction. The eigenfunctions are related to the a kind. I'm sorry. They are related to kind of exponential function of the
So
type.
you mean, okay, sorry for interrupting, but okay,
Yeah.
so eigenfunction of the whole system, or you mean eigenfunction of this operator here?
Yeah.
Yeah, you're talking about the spectrum of this operator, right?
Yeah. What I
Yes.
am asking, can I
Yeah,
use something which is similar to the evolution operator for this
Yeah.
type of problems?
Yeah. That's what I'm thinking also. Yes, you can. I believe you can. You have to find this. So study say, okay, so if I have, yes. So actually, one thing I asked myself along the line of the question you asked me, the comment you make is the following. What I'm interested in is this. So this is a linear operator, right? So I can think about the spectrum of this operator, yes? So now I approximate this Caputo with something. So I'm looking at this new system, right? So I'm interested to see how much the spectral change. What is the difference between the spectrum, right? You either solve this without any approximation, yes? Or replace this with the one I propose. So these are two systems, yes? So I'm interested to see how will this approximation shift the spectrum of the original system. Yeah, you're right. The spectrum can be studied here for this one.
Because in this way you get solution which are which respect the causality condition.
Yes.
I am a poor physicist, so I have just the point of view of the Kramer's chronic relationship to establish the causality. Anyhow, the solution is respect the causality condition, and the use of standard technique can allow a solution. So you can compare with your to try to understand whether the spectral solution is correct and what is the range of validity.
Yeah, thank you for the comment. Yeah, it's very good. Yes, that's another reason why the way by using Herglotz-Nevanlinna is good in the sense that the approximated system itself is causal, also have causality because it's built in this approximation. Because remember, the approximation of the Stieltjes function itself, again, is a Stieltjes function. So this approximation still respects the causality. So both of them, and then, but now we'll just have to see how much it changes spectrum of the original system.
Thank you.
Yeah, thank you.
Good. Many thanks, Yvonne. Many thanks for joining. So it's a small world. So the idea of the whole symposium is to bring people together, people from very different backgrounds. There were not too many biologists today, but yesterday, but we had some very nice talk on the mind and perception and new methods of reality, new sounds, and so on and so forth. So, and that's the beauty of this for me. These were again 2 very satisfying days. And again, I would like to thank all speakers and all attendees for their valuable contributions, including the presentation, including the questions, including the presence. So again, thank you very much. I'm so grateful for all of you. And I hope to see you soon. I will share the presentations in a closed environment to each of you, so you can check. If you want to reach out, you have each other's emails. It can go via me or directly. It's up to you. But I hope that new collaborations will emerge from this. So once again, thank you very much for this very satisfying and beautiful 2-day meeting. And I hope you also enjoyed it. So.
Thank you, John.
Thank you. Thank you, Johan.
Thank
You're
you.
welcome.
Thank
Yeah.
you. It was very nice.
Thank
Thank
you.
you.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.
Bye.
Bye.